Yeah, so good evening guys. So please type in the chat box, is the audio and video fine? So every one of you just quickly please type in the chat box, just confirm the audio and video. Let me just close this window once. Yeah, now it's better. Yeah, so just confirm the audio and video once. It's clear, right? Yeah, good evening all of you. Yeah, it's clear. Great. Okay, so let us start this session. So today is the 4th lecture of this series, English Batch Engineering Math series. Okay, so we are going to have classes at daily 7 p.m. and like today as well. And this is lecture number 4. We have started linear algebra as a first module, and this is lecture number 4 of this particular module. Good evening all of you. Welcome. So can I understand today's lecture? Yeah, it's okay. No issue. You can attend. Okay. Now let's see. Before just going into today's lecture and contents of that, yesterday I have given you some homework. I hope all of you have tried that homework. Did you all try that homework? And it was even telecasted in this Telegram channels of 𝐂𝐤𝐬𝐿 English actually. So this is basically the Telegram channel for 𝐂𝐤𝐬𝐿 English YouTube channel. So whatever happens on this channel and regarding any homework discussions and all, they get posted on your this 𝐂𝐤𝐬𝐿 English Telegram channel, of course. Okay, and this is the link for joining the Telegram channel. You can just scan this link will direct you to the Telegram channel of 𝐂𝐤𝐬𝐿 English. You can just join. Okay, and this is my group actually. If you want any guidance or any personal touch with me, you can just come into this group. That could definitely it's managed by me and my students, of course. So definitely you all can learn together in this group. Okay, so this is for getting in personal contact with me, and this is basically to get all the notifications and all the updates that's going on this channel. Clear? And good evening all of you. So your previous linear algebra one shot can be sufficient. I have slightly updated the content because there were slight changes here and there in the syllabus, so that's the reason. Okay, now let's see this Unity app. So basically if you just type in the, if you just Google Unity PW in the search bar, then you will be redirected to a space where all your doubts can be stored at one place. Okay, so when you're typing your doubt or writing any notes point in the chat box, before typing the note, if you just type #note and if you type the comment, and if you type #doubt and then if you type the doubt, then they get stored in this Unity space. Okay, and for this you can log in with Google, and once you sign in, the page that you'll get is something like this. Okay, so this is how you'll get the page, and this tells you the data about total how many polls you have participated, what is the accuracy of your poll. Okay, and then after all the doubts or note points that you have written during the live classes, you will have a group of all these things at one place. And this is not for a single class or single module. It stores the data for the complete throughout. Okay, once you start, then it stores throughout that time. Clear? So that's what we have. Doesn't it collect our data? It collects. It do collect. Okay, so that's why I suggest you to have a account here. So just log in with your Google account, and then just whenever you're typing doubts, please type, see, whenever I run the poll, you automatically get that. You can type !doubt and then start typing your doubt. Similarly here, !note and then start typing your note, of course. Okay, and then if you see, that's what basically this slides even tell you. Now if you see the last lecture, basically in the last lecture we were talking about the matrix algebra in a bit detail, and also we have talked about this determinants in a much detailed sense. Okay, so we have seen determinants, of course. Matrix algebra is what we have seen to some extent, and then we have started looking at determinants. So we have seen what is a determinant, basically what a determinant can do, and properties of determinants is what we have seen, right? Properties of determinants. Properties of determinants is what we have seen, and we have solved some questions basically as we went toward the poll, and I have given you some homework for roughly 4 to 5 questions. Did you all solve those questions? Yes or no? So please type in the chat box. Did you all solve the questions what I have given you as homework? They were in fact circulated in the Telegram channel as well, so I hope all of you had gone through that questions, right? So if you have solved these questions, then for this question I am giving you just 30 seconds. Whoever has solved, they just enter the answer. Come on, whoever has solved this homework question, they can just enter the answer. The poll is active. If you have already solved this, then you know the answer of this question by default, so within 30 seconds you can just enter. (49) is coming as the determinant. Maybe it could be possible. Sagnika, good. Chalo. Let's solve this question. First of all, if some of you have entered, solve this, then let's check what's the answer. The maximum value of the determinant among all 2 by 2 matrices, real symmetric matrices with the trace 14 is dash. Okay. So let us take a matrix A. Let A is equal to, it's a 2 by 2 real symmetric matrix. So you take A, B, then if you take B here, to matrix for the matrix to be symmetric, this element is also B, and you have C here, correct? This is a 2 by 2 real symmetric matrix if all the elements are real. Of course, there is also different types of matrices and complex numbers like the Hermitian, skew Hermitian, all these things, but we don't have any PYQs in the common branches that we deal. So we are not talking about the Hermitian or the skew Hermitian matrix intentionally, okay? Because I don't want to stress the syllabus. The syllabus already is big, so let us just confine ourselves to the syllabus actually, okay? Now let's see, this is a real symmetric matrix. Now it is given out of all such matrices which can be formed such that trace of A is 14. Okay, so trace of A is equal to 14. This tells you your A plus C, which is trace, is 14, of course. Okay, so if A plus C is 14, so where the notes uploaded in the Shreya, basically in the link that's given in the description, it directs you to the batch actually. Okay, there's a free batch that we have created in the PW app. So if you click on this link will directly take you to the batch where all the notes, everything is being uploaded. Okay, now let's see, this is A plus C is equal to 14. Now they're asking what is the maximum value of the determinant? Maximum of AC minus B square, this is the determinant, if A plus C is equal to 14. This is what they're asking. Yes or no? Please type in the chat box. They're asking the maximum value of the determinant. Okay, so what could be the maximum value of the determinant is what they're asking you. So please type in the chat box. Is this clear to all of you? This is what they're asking. We'll see how to solve, but this is what they're asking. Is it clear to all of you till this point? Okay, whether you have solved or not, it's fine, but this is what they're being asked. This is what it's being asked in this question. Okay, now let's see. First of all, if this value has to be maximum and this is a real number, tell me for AC minus B square to be maximum, since you know this term is being subtracted from B square, correct? So let's say AC minus B square is what we have. If this term has to be maximum and if B is a real number, then ultimately B square is always greater than or equal to 0, because B is a real number. B is not complex, so B is a real number, so B square is always greater than or equal to 0. If this term has to be maximum, then the term which you are subtracting it should be minimum, which means B has to be 0. Yes or no? Will you all agree with me? Yes, because if I want to maximize this term, then ultimately this term is being subtracted from this total, from this AC, and the maximum value or the minimum value of B is actually 0. So this subtraction part has to be minimum, so B has to be 0 actually. Okay, now if B is 0, then we want maximum of AC if A plus C is equal to 14 actually. Okay, now you can apply your principle of maxima and minima, like the first derivative being 0, or you can, since I have not taught this principle of maxima and minima yet, you can use one thing. All of you might have studied one particular thing: arithmetic mean greater than or equal to geometric mean. Have you studied this? Yes or no? If there are two real numbers AM and is AM, if there are two real numbers A comma B, of course being positive, then this A plus B by 2 is always greater than or equal to square root of AB. Do you know this? Correct? Yes or no? 2. Now let's see, if you know this, that means it tells you that A plus C by 2 is always greater than or equal to square root of AC, and A plus C is given as 14. 14 by 2 is greater than or equal to AC. This implies AC is less than or equal to 49, because this is 7, of course. Okay, if you square on both sides, AC is less than or equal to 49. That's it. Okay, so the maximum value of this term AC is actually 49. That's nothing but the determinant of this case, which is 49 here. Okay, that's all. If you don't know this point, arithmetic mean greater than or equal to geometric mean, you can work out using basic calculus. Look, I'll just give that also. Maximum of AC if A plus C is equal to 14. Okay, so now let's say my function f of A is equal to a into c. C I can replace with 14 minus a again. So this is my function. Now I want to calculate maximum value of this function, correct? So how we will do? D by dA of f of a is equal to 0. This implies a into minus 1 plus 14 minus a into 1 is equal to 0. So a equal to 7. This is what you get. So this is the stationary point for this function if you calculate the first derivative and equate it to 0. Now if this is the a equal to 7, if you calculate second derivative, this is actually 14a minus a square. So 14 minus 2a equal to 0. So a equal to 7. So what is second derivative? D square by dA square of f of a. The second derivative of this function is actually, first derivative would be 14 minus 2a. So second derivative would be minus 2, which is negative. That means this function has a maximum value at this a equal to 7. Okay, since second derivative is 0. Anyhow, I'll touch up all these concepts again when I'm talking about single variable calculus. But right now, just since I hope all of you have studied how to calculate maximum of any single variable function, so I'm just taking the advantage of that knowledge. That's it. Okay, otherwise I will generally teach all these things in the single variable calculus and then we would progress. Okay, now since this is negative, second derivative is negative, this implies f of a is maximum at a equal to 7. So this implies maximum of f of a is equal to 14a minus a square at a equal to 7. So if you put a equal to 7, 14 sevens are 98 minus a square 49, which is 49. So in this way also, by using the principles of single variable calculus, you can go for this 49. Okay, that's what. Got it? Is this clear to each and everyone? Did you all understand how we have worked out the things? Yes or no? Please type in the chat box. Is this clear to each and every one of you? Okay, so this is using basic calculus. If you don't have the idea of calculus, you can even go with these points of arithmetic mean greater than or equal to geometric mean. That's it. Do anyone know how this comes up? Do any one of you know how this value actually, how this inequality can be proven? Why arithmetic mean greater than or equal to geometric mean? Do you know? Do any one of you have seen any time? No? Yes? Nothing? No? Okay, I can I'll spend 1 minute to show how arithmetic mean should be greater than or equal to geometric mean. Why arithmetic mean greater than or equal to geometric mean? So like you all know, for two real numbers a comma b, for two real numbers a comma b, you know a plus b whole square is always greater than or equal to 0, correct? A plus b whole square is always greater than or equal to 0, of course. Okay, and if you just work it in the reverse fashion, similarly a minus b whole square is also greater than or equal to 0, of course. Okay, now if you, for example, if you consider this a plus b by 2 whole square, this value consists something more than ab all the time. The reason for that is this term is actually a square plus b square by 2 plus 2ab by 2. So we can get, just a minute, this is 4, of course, a square plus b square plus 2ab by 4 of course. Okay, now clearly you can check this a square plus b square by 4 plus 2ab, and this term can be written as a minus b whole square plus 4 plus 2ab. This is what we have, by 4, and this 2ab by 4 is as usual. So now you can see ab by 2, ab by 2. So ab by 2 and ab by 2, this is always greater than or equal to ab because of this term. That's it. Okay, so this inequality always holds. You can just simplify. If you just simplify this expression, then you can find out this a minus b whole square term will either be 0 if a equal to b, or it will always give some positive value, and this summation itself is ab. So this ab plus something is always greater than or equal to ab, which we can deduct from this. That's it. Okay, since this a minus b whole square is always positive, I have given this. That's all. Okay, that's how you can show am greater than or equal to geometric mean, just by simplifying. Okay, then let's go to the next question. So this answer has got 49. 49 is the correct answer. So I think only 𝐂𝐚𝐿𝐿 has answered anyway. Let's see. 49. Continue. Okay. 𝐂𝐚𝐿𝐿. Yeah. Good. So let's go to the next question quickly. So for x and y are non-zero square matrices of size n by n. If xy is equal to a zero matrix of size n by n, this is not m by n, sorry, this is n by n, then which of these following will happen actually? Okay. So if you have solved this question, again, you could answer in 30 seconds. Come on, solve this. Just enter the answer. D is coming. Det x not equal to 0 and determinant of y not equal to 0. That's what you're getting. If x and y are non-zero square matrices of size n by n. So I told you product of two non-zero matrices can be a zero matrix. That's what it's given here. xy is equal to 0. Then which of these things will happen actually? Quick. 𝐂𝐚𝐿𝐿, Abdul, Thomas, Kids Gaming, Suresh, Danush, Vasishta, Arya, and all. Okay, done. So let's see. First of all, I just want to tell you one thing. Solution. Given x not equal to 0 and y is not equal to a null matrix, of course, sorry, this is not 0 actually, this is null matrix. Okay, x not equal to a null matrix and y also not equal to a null matrix. Then, but xy is actually a null matrix actually. Okay, this is what you know. Now let's see, they have given you determinant of x equal to 0, determinant of y not equal to 0. So first of all, if you apply determinant on both sides of this equation, determinant of x y is equal to determinant of 0. So this implies determinant of x into determinant of y is equal to determinant of null matrix is 0. Now since these two are scalars, this is a scalar, determinant of matrix x could be some number. Similarly, determinant of matrix y should also be some number actually. Okay, so product of these two numbers is actually equal to 0. So like it's equivalent to writing a into b equal to 0. So either a equal to 0 or b equal to 0 actually. Okay, so this is what you get, a equal to 0 or b equal to 0. In scalars, this is what it's to. But in case of matrices, there is one thing which you should understand here. Look, I'll tell you. First of all, x not equal to 0, of course. Okay, non-zero square matrices of size n by n. Look, if these are non-zero square matrices, let's say case 1, let det x not equal to 0 and det y equal to 0, for example. Okay, so let's say I have taken this case because if that equation has to satisfy, there are three possibilities. One possibility is determinant of x is 0, this is non-zero, then also this product is 0. Det x is non-zero and det y is 0, then also this product is 0, and both are zeros. In such case also this is 0. Means as of now, if you want to satisfy this equation, any of this first three a, b, c could be possibilities. Yes or no? Correct? If this happen, then this equation gets satisfied. If this happen, then also this equation gets satisfied. If this happen, then also this equation gets satisfied. Apart from D, it could be any of these three things. But now let us see what happens here actually. If det x not equal to 0, this implies x inverse exists. Correct? 2. Can I say this? If determinant of x is not non-zero, that means x is non-singular and it's a square matrix clearly. So x inverse should exist. Then we have xy equal to 0. This implies since x inverse is existing, if I multiply x inverse on both sides, this tells me x inverse times x, because matrix multiplication is associative, and 0 into any matrix gives you, null matrix into any matrix gives you a null, and this x inverse x is nothing but identity matrix. So I into y gives you y is equal to 0 actually. Okay, so this y equal to 0 is what we are getting if you do this simple analysis. But this is actually contradiction to the given question, because clearly they have told you y is not equal to 0, but this simple calculation tells you that y is actually 0. That means this cannot be a possibility. Okay, because if you take this as possibility, if x inverse exists, that x inverse is proving that y equal to 0, which is not true actually. Okay, if you go for case 2, let det x equal to 0 and det y not equal to 0. If you do a similar job, you will end up x equal to 0. Like let's see, this implies y inverse. Correct, y inverse exists. This implies xy times y inverse is equal to 0 times y inverse. This implies x is equal to 0, which is also wrong, again contradiction. Okay, So this is also a contradiction. X is equal to 0 is what you got, but clearly we know X is not equal to 0. So this possibility should also get eliminated. Okay, so then one thing what we do is ultimately both determinant of X and determinant of Y should be zeros. You can check, like in every case what I have given you, like in the case of nilpotent matrix, or basically in case of like general examples I have given, whenever I have shown you product of two matrices, product of two non-zero matrices is a zero matrix, ultimately the determinant of these two matrices is 0. Okay, like for example I have told you on the day 1, A 0 0 0 0 0 0 B, these two are non-zeros, but if you multiply they'll get a zero matrix. Clearly the determinant of this matrix is 0, this matrix is also 0. Okay, so in this case it's not enough for you to have one of the things to be 0, but both are actually 0. Happy birthday sir, today is not my birthday. Yeah. Why do we multiply its inverse on both sides? What is the cause of this? Because to show that this actually contradicts. Okay, that's what, to show that this don't help you out. So that's why we have actually multiplied this, to show that this arises a contradiction to the given thing in the question. Clear? So that's why if product of two non-zero matrices is a zero matrix, then definitely both the non-zero matrices are singular matrices. Okay, that's what. Clear to all of you? This point is very important point actually. Okay, few times even in eigenvalues this point is very helpful, even in calculating ranks. Okay, this point is very helpful to you. Clear? So I would like to give one summarization point here. If product of two non-zero matrices A and B is a zero matrix, then both A and B must be singular matrices. Must be singular matrices actually. Got it? Is this point clear to all of you? Because some of you might have thought that if determinant of X equal to 0 and determinant of Y not equal to 0, or maybe vice versa, could just satisfy that X into that Y equal to 0, but fundamentally that do not satisfy the given conditions in the question. Okay, so that's why both should be zeros. Clear? Okay, is this point clear to all of you? Because this point is very important point. We use it many times in calculations of ranks. Okay, and maybe in eigenvalues a lot of times. Is this clear to each and everyone? Yeah, both should be singular. Okay, then let's go to the next question that I have given you. If A is equal to this particular matrix and adjoint of A equal to this, then what is the value of K? Come on, again. For the previous question, C is the correct answer, of course. None of you have marked, all of you have marked D. Okay, fine. For this question, integer type, again, enter the answer if you have typed in the chat box. So if you have solved this question previously, because it was a homework question, so just type the answer if you have solved this question. Quick, faster. -5 is coming. Okay, maybe I don't know. Let's solve and check it up. It's a PYQ. Okay, all these questions what I am solving in this batch are previous year questions. Okay, because I don't want to make the life complicated in the beginning itself. So in this course, along this course, I would like to solve only PYQs. Okay, so that you have some basic idea on what kind of questions are turning up in GATE examination, and then maybe in the upcoming series, like maybe some practice solving or practice sessions or things like that, we will go for some new questions. Okay, then let's see. So anyway, let's see. You have got A is equal to 1 minus 2 minus 1 2 3 1 0 5 minus 2. This is what you got. Okay, they have also given you adjoint A. So adjoint A is equal to -11 -9 1 4 -2 -3 10 K 7. Okay, now they want you to calculate what is the value of K, and many people I know they might be interested to find out what is the basically what is the adjoint of this matrix. Okay, so that takes a lot of time for you. Okay, because if I give you a 3 by 3, then calculating adjoint will definitely take some time, and ultimately that way of solving could not be fit for gate examination because it takes around 4 to 5 minutes. Okay, now let's see what else you can do. First of all, we all know one thing: a into adjoint A will give me something like det A into identity matrix, correct? So this det A times I have shown you how this comes up in the last class. So A into adjoint A equal to det A into I. Now if you multiply this A with adjoint A, ultimately you will get a matrix of size 3 by 3. This is 2. You'll get a matrix of size 3 by 3. Now can anyone tell me, if this is an identity matrix, I mean some scalar matrix, det A, and all other elements are zeros, then this element would be 0. In fact, any of these elements would be zeros if they are on non-diagonal elements. Okay, then let us focus on this element. To get this element, what you'll do, first row multiplied with second column, because I want to involve this k, that's why I have chosen this element. Okay, so if you multiply this first row with this second column, okay, then ultimately you would get 0 here. Okay, because that's the result. Now if you multiply, let's see what you'll get. This implies 1 into minus 9, minus 2 into minus 2, plus 4, minus 1 into k, minus k equal to 0. So this tells you minus 5 minus k equal to 0. So k equal to minus 5. That's it. K equal to minus 5. You can in fact check any of the see, the other element which involves k is basically this element, okay, and the other element which involves k is basically this element. In fact, you can check this 0 or this 0. Even if you check this 0, you will get k equal to 5. If you check 0 into minus 9, 0, 5 into minus 2, minus 10, minus 2 into k, so minus 2k is equal to 0. So this also gives you k equal to minus 5. In fact, you can check any of the things. I don't suggest you to check this element, because if you want to check the value of k using this element, you should calculate the determinant of this matrix, which is again an extra calculation. That's why you can eliminate that possibility. But whereas by checking this element or this element simply, you can get k equal to minus 5. Clear? Why it's 0? Because if this is an identity matrix multiplied with scalar, this could give you something like determinant of A 0, 0, 0, det A 0, 0, 0, det A. That's it. Okay, so that's why this element and this element, they are zeros. Clear? Rather than calculating the complete adjoint, just if you multiply that corresponding row with the corresponding column, you can figure out this k value is equal to minus 5. Okay, fine. Please type in the chat box here. Did you all understand this or not? K equal to minus 5. I know people are busy in calculating adjoint here, but no need. Okay. How many of you tried calculating adjoint here? Please tell me. Honestly, please tell me how many of you tried calculating adjoint of the matrix and tried to get the value of k? How many of you have tried calculating the adjoint of A and then try to observe the value of k actually? You have done, Abdul? I know there are people who might have tried this, but these kind of things could save a lot of time actually. Okay, so clear? Yeah, it's okay. Minus 5. So anyway, pole again. Pole, if you check, where is the pole? Minus 5. Okay, but where is the option for minus 5? Minus 5. Negative numbers cannot be 100. Is it? 5 with a negative sign, but of course minus 5 is the correct answer. I know this is wrong, but I know I have seen people entering minus 5, so yeah, 2. Okay, so minus 5 is the correct answer. Then one last question which I have given you in last class. The equation, so this is an equation equal to 0, represents a parabola passing through the points of, let's see. Okay, so again, if you have solved this, you could enter this answer quickly. So it could be finding determinant by multiplying elements with cofactor and solving. Yeah, you can do that. Okay, you can just calculate the cofactor of A to 3. Yeah, you can do that also. Okay, but when two matrices are visible side by side, it's always better to do row with column so that you get direct answer. Okay, Vivek. So anyway, solve this question quickly. Faster, a bit fast. Fine. Okay, guys, before solving this question, I just want to give you one information. Vector spaces and actually I deal vector spaces in vector algebra chapter, but since some of you are only from CS or data science, so I'll teach vector spaces and partition matrices especially, okay, block matrices and all we'll cover in the last lecture, okay, because hopefully in tomorrow's class we'll solve system of equations and eigenvalues, eigenvectors, diagonalization, these kind of stuff. So then we'll progress to the last lecture with vector spaces and partition matrices, okay, no issues, because if I keep it here again it's like some discontinuity in the thing. But of course I'll tell you one important point here, but then we'll look at vector spaces, span, all these things in the upcoming lecture, which is the 6th lecture of this module, okay, on Saturday. Chalo, look, let's see here. Solution: given the equation of a parabola is given by 2 1 1 1 1 minus 1 y x square x is equal to 0 actually, okay. Now ultimately subspaces, yeah, of course subspaces also, okay, that's what a vector space will definitely have a subspace. We'll deal all the subspaces. Now let's see if this is 0, okay, so this is 0, 2 1 1 1 1 minus 1 y x square x. Now ultimately if this parabola is let's say for example this parabola is passing through this set of points for example, okay, then ultimately these 3 points should satisfy this determinant, yes or no, correct? Will you agree if I say that if this parabola is passing through all these points, then definitely each point should satisfy this determinant? Yes, will you all agree with this or not? Correct? Yeah, let's say if this parabola is passing through x comma y, then definitely point x comma y should satisfy this determinant, correct? Now let's see, you can go with the options also, or you can have different techniques to do this. Look, first of all, if you check this option 0 comma 1 for example, okay, so if you check 0 comma 1, let's see what happens, okay. If you want you can solve this also, but anyhow options are given, so we'll go with options verification. Option A, if you put 0 comma 1, 2 1 1 1 1 minus 1 0 comma 1, so 1 0 0, that's what you have, okay. So this is 1 0 0. So if you take determinant 2 times of 0 minus 1 into 0 plus 1 plus 1 into minus 1, so this gives you minus 2, which is not equal to 0, okay, which means this point 0 comma 1 is not passing through this parabola. So definitely this option is wrong, because if there are 3 points and if one of them is not satisfying, then it doesn't matter whether the other 2 satisfy or not, okay. So we are deleting this option because the first point 0 comma 1 itself will not satisfy this determinant, because you can clearly see 2 times of 0 minus 1 times of plus 1, because minus of minus 1 will be plus 1 plus 1 into minus 1, so which is minus 2 of course. Now coming to option B, let's check. If you look at option B, so 0 comma 0, look, first of all without doing you can tell 0 comma 0, if you put x equal to 0 and y equal to 0, this complete row of this determinant becomes 0, okay. If one complete row of a determinant becomes 0, then ultimately determinant value is 0, correct? Yes or no? Because if you write the expansion of cofactors about this third row, then ultimately 0 into cofactor of this 0 plus 0 into cofactor of this 0 plus 0 into cofactor of this 0, total it will be 0, determinant value is 0 actually. Yes, did you understand? If one complete row or one complete column of a determinant is 0, then ultimately multiplying those zeros with the cofactors will still give you 0, so the determinant value is 0 of course, okay. So that's why 0 comma 0 satisfies this determinant, okay. Now coming to minus 1 comma 1, if you put x equal to minus 1 and y equal to 1, what happens? If you put x equal to 1 and y equal to 1, sorry, x equal to minus 1 and y equal to 1, this x equal to minus 1 will make this minus 1, minus 1 whole square will be 1, y is again 1, so this row becomes 1 1 minus 1, then ultimately these two rows become identical, then also the determinant value is 0 of course, okay. Then if you replace 1 comma 2, if you put x equal to 1 and y equal to 2, this becomes 2 1 1, then this third row matches with the first row and ultimately first and third rows become same, so even in that case the determinant value is 0. So all these 3 points satisfy that equation, so option B is the correct answer actually, okay. Now coming to option C, 0 0 can satisfy this, but 1 comma 1 will not satisfy. If you want you can check. Similarly here 0 0 satisfies, 2 1 will not satisfy, 1 2 will actually satisfy, but this point will not satisfy this, so D and C are the wrong answers actually, okay. That's why just by using options verification you can tell, or you can also tell it using one more technique. If you expand this determinant, if you expand this determinant, let's see what you will get. 2 into x plus x square minus 1 into x plus y plus 1 into x square minus y is equal to 0, okay. So if you simplify this expression you will get parabola, of course, 2x minus x, so we have an x, then 2x square plus x square, you have 3x square then minus y is equal to 2y. So y equal to 1 by 2 times of x plus 3x square. This is the equation of the parabola. Okay, then you can check which points are satisfying this parabola. This is also one more way to solve this. Clear? You can have multiple ways to solve things actually. Got it? Fine. Yes or no? Please type in the chat box. Is this clear to each and every one of you? Okay. I hope it's clear, right? Yeah. Now, so if you go for the options, it's B. Yeah, 2. Of course, 100. Ashwini, Sagnika, good. So if you see the leaderboard, Sagnika is on the top, attempted 4. Then Ashwini, Abdul, good. Okay, nice, fine. So now let's once check minus 1 comma 2. Minus 1 comma 2 will definitely not satisfy. Okay, because you can see this minus 1 will be actually negative of this, but this one, because you may observe, you may feel that this first and third are identical when you put minus 1 comma 2, but this will be minus 1 and this will be plus 1. So there is a minus 1 and plus 1 difference in the last column, so that's why it won't be 0. Okay. Method 2. In this method 2, you want me to check y equal to minus 1 comma 2. Minus 1 comma 2 will not satisfy it, because anyhow minus 1 comma 2 is not there in any of the options. Minus 1 comma 1. Okay, minus 1 comma 1 if you keep, then minus 1 comma 1, then 3 plus 3 minus 1, 2 by 2, if you cancel you have 1. So minus 1 comma 1 will satisfy this equation, right? Yeah, it's satisfying. You can see if you put x equal to minus 1, this turns out to be plus 3, this is minus 1, 3 minus 1 is 2, 2 by 2 is 1, and ultimately y is 1. Okay, this satisfies for minus 1 comma 1. This equation gets hold for minus 1 comma 1. Clear? Okay, then let's get into the things. So basically today I plan to cover concept of a rank and also system of linear equations, but we'll see how we progress. Okay, then before going forward, I just want to give you 2-3 important points about determinants. If determinant of a n by n matrix is det A, it is denoted by this, then determinant of adjoint of A. This is a bit important actually. Sometimes questions came on this also. So what is the determinant of adjoint of A? Okay, so here to calculate the determinant, they don't give you A. Okay, so means basically you cannot calculate what is this matrix. Okay, so just by knowing this det A and this n, you have to figure out something. Okay, because you cannot calculate adjoint of A because this capital A, matrix A will not be given. Okay, so then let's see. This value is actually det A whole power n minus 1. Okay, so how this comes up? It's very easy again. So look, we know we have A times adjoint of A equal to det A times identity matrix, of course. Okay, now if you take determinant on both sides, then you know det A into det of adjoint A is equal to, then this det A is like a scalar. Okay, determinant value is some finite number. So this scalar, if you want to take out outside this determinant, then this is a sign n by n. Identity matrix will be of size n by n ultimately, because A is n by n, then ultimately adjoint A is n by n. If you multiply two matrices, you will end up with a n by n matrix. So if you want to take this scalar out, then we have det A whole power n. You remember in yesterday's class I was telling this property, determinant of k into a n by n, where k is scalar, can be written as k power n times det A. We have talked about this. Okay, then this is determinant of A. If you take out of the determinant, then det A whole power n is what it turns up, and determinant of identity matrix is what you will get. Okay, and anyway this value is 1, of course. So det of adjoint A is equal to, this is det A and that's det A power n. So if you cancel det A, we have det A power n minus 1 actually. This is what you have. Clear? So det A whole power n minus 1 is the determinant of the adjoint of a matrix. Okay, so this property is again important because there were some 3-4 questions in previous years which came on this particular point. Okay, so det of adjoint A is equal to det A whole power n minus 1, of course. Then let's see, if I ask you what is determinant of adjoint of adjoint A. Okay, so sometimes we will have a double adjoint. Then what is the case? Okay, so this value is nothing but we have determinant of adjoint A is equal to det A whole power n minus 1 square. Okay, so first you calculate this n minus 1 square, then raise to the power. Like it's very simple. Look, let B is equal to adjoint A, for example. Okay, if B is adjoint A, then ultimately we have B into adjoint B is equal to det B into I. This gives you det of adjoint B, like the previous whatever we have done here. If you do it same for B matrix, now we have det of adjoint B is equal to det B whole power n minus 1. This is what you'll get. Okay, but what is B actually? Adjoint A, correct? That's what we have taken. So if you replace B with adjoint A, det of adjoint A is equal to determinant of B is nothing but determinant of adjoint A, which is det A whole power n minus 1, this whole power n minus 1. That's it. Okay, so n minus 1 power n minus 1, it's like a power mn. So n minus 1 into n minus 1 gives you n minus 1 square. That's it. Okay, so det A whole power n minus 1 square is what you'll get. Adjoint A again here. Clear? So this is the term which is again important. Similarly, if you have one more adjoint, it comes up cube because this process keeps repeating. That's all. Clear? Okay, because since this loop just keep repeating, so if you have one more adjoint here instead of 2, you will end up with 3. That's all. Okay, is this clear to all of you or not? Please type in the chat box. Okay, yes or no, guys? Please type in the chat box. Is this clear or not? Quick, be fast. Come on, type it a bit fast in the chat box. Yeah, clear? Now let's see few more things actually. Calculating the transformation matrices. Calculating the transformation matrices. Calculating the transformation matrices, which is actually very important. Okay, so how n minus 1? Here you'll see there is one det A and det A whole power n on this side. So if you bring this det A here, det A cancel this power n minus 1. A cube by A is A square, correct? That's what. Okay, then let's see. We know one generally what we have is, if you have a vector x and if you operate it with a matrix A, then you will end up with another matrix y or another vector y. Okay, now if this is given and this is also given, if A and x both are given, you know how to calculate y. Just multiply, you'll get y. Now my question is, if I give you x and if I give you y, and if I ask you what matrix will actually convert this x to y. Okay, did you understand the difference in the question? Previously we know both A and x, so that if you multiply you'll get y, of course. Okay, so what we have done basically the matrix multiplication and all. But now if I ask you, for a given vector, if this is how I want my transformed vector to be, then what should be the matrix that I multiply this x so that I have this y. Okay, so you have to calculate what is this transformation matrices. That's what. Did you understand what we are doing? And this kind of things are very important actually. Okay, if you go for physical things, okay, like basically if you go for physical subjects like you know, fluid mechanics or any even in solid mechanics we use it a lot of times. Okay, so this transformation matrices are very important, and in chemistry also especially. Okay, you have stereomers, all these cases. Okay, so let's see how we do this. Example, I'll start with a simple example. A matrix that reflects a vector about y axis. That reflects a vector about y axis, for example. Okay, so a matrix that reflects the vector about y axis. Like you can see, you have x and y. In 2D I am taking so that the job is easy to geometrically show. Fine. So let's say this is x and this is y. Then so let's say this is my vector a comma b, or let's say x comma y. Directly you take x comma y. Now let's say when you multiply this vector, this is x, let's say. Now when you multiply this vector with a particular matrix, this vector gets reflected about y. Okay, the reflection of x, the reflection of this vector x bar with respect to this y axis would look something like this. It looks something like this. So ultimately this coordinates, if this is just reflected, which means this point has got reflected about y axis, the coordinates would be minus x comma y. Yes or no? Will you all agree? If I reflect this vector about this y axis, my coordinates could be minus x comma y actually here. Yes or no? Type it in the chat box. Okay, minus x comma y, of course, that's what. Okay, now let's see, if you take a matrix, since you don't know the elements, let A is equal to A, B, C, D, of course. Okay, then we know Ax is equal to, so this is my y vector which is obtained by transformation. So Ax is equal to y. This implies A, B, C, D. Then after, initially it is xy. Now this got transformed to minus x comma y here like this. Okay, now we can figure out these elements just by equating the equation. You can see Ax plus by Cx plus dy is equal to minus x comma y, of course. Okay, then you can observe, see, if two elements of a matrix, or if two matrices are equal, then ultimately the corresponding element should be same, which means this Ax plus by should be equal to minus x and Cx plus dy should be equal to y, of course. This implies A equal to minus 1, B equal to 0, C equal to 0, D equal to 1, of course. Okay, if you put C equal to 0 and D equal to 1, only then this element will be equal to this element. Similarly, if you put A equal to minus 1 and B equal to 0, only in such case this element would be equated to this. So the matrix transforming is A, B, C, D is going to be minus 1, 0, 0, 1. Yeah, so this is the matrix actually here. Clear to all of you? So this matrix will actually transform this as a reflection about y axis. Clear? Similarly, if the reflection is about x axis, for example, okay, if this is a vector, if you want to reflect about x axis, coordinates would have been x comma minus y. So if coordinates are x comma minus y, this vector is x comma minus y, then again you will perform the multiplication and get the values of a, b, c, d. Clear? Now we will see one last case before we move on to the concept of rank. A reflection, a matrix that reflects about the line y equal to x. A matrix that reflects about the line y equal to x. Okay, so let's see, if you have so this is your origin, for example, and you know you have your x axis, y axis, and let's say the line x equal to y is passing. Okay, so this is the line x equal to y, of course, or y equal to x maybe. Then let's see, if you have a point, x comma y here. Okay, so this point is x comma y. If this point is x comma y, then if you reflect this, say something like this, then ultimately this coordinates, you don't know what are these coordinates. First of all, let's say alpha gamma beta actually. Okay, alpha gamma beta. Then and ultimately, basically what I mean is, if you have a vector like this, then let's see, if this is the vector x, because in our classical terminology we are denoting with x and y. So if this is my x, and then ultimately this is my y, for example, then which matrix can actually make this rotation x, can actually keep this x to y actually, okay, such that this point will actually get this from this location to the reflection about the line x equal to y, of course. Okay, so is any question bank or workbook is available for practice? Basically PYQs is there, and in the Telegram channel what I have posted, daily we are placing some homework questions. Okay, so please go to the homework questions so that you have some idea, okay, on the topics that are taught in class. Okay, clear? Now let's see. Fine, anyway, this is just the case. Now can anyone tell me what are the coordinates of alpha comma beta? Do anyone have any idea? What could be the values of alpha comma beta? If you reflect a point x comma y about the line y equal to x, what points you'll get here? Any idea? To any one of you? If you reflect a point x comma y about the line y equal to x, what could be the coordinates of the reflection? No idea? It's okay if you don't have any idea, it's fine, but if some of you have any idea, you can just try it. See, when I'm asking questions now, please at least give a thought about it, okay? Because see, teaching is just not to make students listen, okay, what faculty is teaching, but make them think, okay? You should develop this power of thinking. If you cannot think, then you cannot do well actually, okay? X comma minus y, no, wrong, okay? Because the reason is, yes, exactly, Asad, y comma x. These points are y comma x actually, okay? So this coordinates would be y comma x. Means basically alpha value is y and beta value is x, of course. So आपको JEE advanced की questions हल्के लगते होंगे, फिर से IIT कर लो. I'll try, okay? Because previously before teaching it, I actually taught JEE advanced, but of course long back, okay? So I have taught that for 2.5 years roughly, and then slowly I moved to GATE, okay? Because in what I found is like, let's say when I'm teaching JEE advanced physics, okay, I'm teaching maths and physics both. So whenever I'm teaching, I felt like I cannot teach all the content what I know, of course, okay? Because like if you see fluid mechanics at BTech level, okay, or thermodynamics, heat transfer, these kind of subjects at engineering level, we can teach more, okay? We can teach many beautiful concepts, but JEE advanced syllabus is limited or restricted to that point where you cannot go beyond certain things. So I've shifted towards GATE and started teaching maths. Then after, you know, mechanical related subjects, of course, okay? My specialization is normally in thermal, so I teach normally thermodynamics, fluid mechanics, heat transfer, these kind of subjects in day-to-day GATE batches, okay? So that's what. Anyway, we'll see. OUTRD something, I couldn't pronounce it, sorry, but I'll try that, okay? So anyway, this is alpha comma beta. Now how we can show that this is alpha comma beta? That's the main question, okay? So people who know it, it's fine, but people who don't know how these coordinates are y comma x, I'll ask you one thing. If you, let's say I don't know y comma x, okay? So first of all, I don't know it's y comma x, so I have to calculate what is alpha and beta. Let's tell me, if this is x comma y and this is alpha comma beta, then definitely the midpoint of these two will definitely lie on this line y equal to x. Yes or no? Correct? If these are the 2 points and this point is obtained by the reflection of this point, then the midpoint of these two will definitely lie on this line x equal to y, of course. Correct? Yes or no? Will you all agree with me if I say this? If you have a mirror and if you are reflecting, ultimately the distance between the point of reflection or the point of source and the mirror would be same as mirror and the point of reflection. Correct? You don't say it inside the mirror if you check. Yes? So ultimately, if I calculate midpoint, you know, midpoint calculation, midpoint would be x plus alpha by 2 comma y plus beta by 2, of course, okay? Now, if this is x plus alpha by 2 and y plus beta by 2, and this midpoint, so does reflection means rotation? Yeah, of course, 2, okay? Without changing the length, we are actually rotating. That's it, okay? Now, let's see. If this is x plus alpha by 2 and this is y plus beta by 2, this point should lie on the line x equal to y, which means these two coordinates should be equal, okay? So this implies since midpoint lie on y equal to x, this implies x plus alpha by 2 is equal to y plus beta by 2, of course. So this tells you x minus y is equal to beta minus alpha. This is one equation, fine, because you have two unknowns, okay? Alpha and beta are two unknowns, so you need two equations to solve them. So this is one equation. Can anyone tell me what could be the other equation? One equation, clearly midpoint, so midpoint should be lying on that line. So can you tell me what could be the other equation actually? How I can get the other equation? Because I need two equations, okay? There are two unknowns, alpha and beta. I need one more. So can anyone suggest me something? How I can get one more equation? How I can get one more equation? Anything? Any hint you can give me? Can you think of anything? Come on, I'm waiting for comments in the chat box. Quick, a bit faster. Length will be same. Okay, yeah, 2 length can be same, but more than length, yeah, perpendiculars could actually do the business. Okay, clearly if it's a reflection, then this angle would be 90. Okay, if this angle would be 90. Now clearly this line has a slope equal to 1, you know, y equal to mx, so m is 1 of course, so this slope is actually 1. If these two lines are perpendicular and you know the slope of this line is 1, what would be the slope of the line AB? For example, if I call this AB, what is slope of AB? Slope of AB would be equal to -1, correct? Yes or no? Slope of AB is equal to -1 of course. So slope of AB equal to -1, this implies y to -y1, you maybe take the first point as second point, I mean that x comma y, a as the second point, so y minus beta by x minus alpha equal to -1. So this tells you x plus y is equal to alpha minus beta. This is what you get if you simplify this. Okay, so x plus y is equal to alpha plus beta is what you get. Okay, so this is equation 1 and this is equation 2. So ultimately if you add these two equations, y gets cancelled, 2x is equal to alpha also gets cancelled, so 2x equal to 2 beta, so ultimately this beta value is x. Similarly, if you put beta equal to x in this equation, x minus y equal to x minus alpha, so y value is alpha, or alpha is y of course. That's how you get the coordinates of the reflected point. Okay, clear to all of you? Did you understand how the reflected points are y comma x? Okay, simple bit of basic knowledge of maths. That's it. Okay, and then if you apply this transformation, a b c d x y is equal to, finally my coordinates are turning up to be y comma x, so this tells you ax plus by cx plus dy is equal to y and x. So this tells you ultimately your a b c d is equal to the matrix which is equal to 0 1 1 0. So this matrix will actually provide a rotation, a reflection about the line y equal to x. Clear? So these are the things. Okay, then I'll ask you one question. Basically, do you know, if I ask you ax plus by plus c equal to 0, what is the slope of this line? What is the slope of that line? You know, it's a linear equation. Basically, if you plot it on a 2D, you'll get a straight line. What is the slope of that line actually? Ax plus by plus c equal to 0. If you plot it on a straight line, what is the slope you'll get? Fast. What is the slope of that line ax plus by plus c equal to 0? Minus a by b minus c by a minus a by b minus b by a. Do x has to do something with orthogonal matrix? As we studied, rotates without length change. It does. Okay, but we don't know what is the exact value of theta. Okay, that's what. Minus a by b or minus b by a? Minus a by b or minus b by a? Any confusion? See, I'll just tell you one thing. You know, slope is nothing but dy by dx. Correct? Slope is nothing but dy by dx, because I'll explain you when again I come back to calculus. I'll deal it in a bit understandable way, in a much more elaborated way. If you differentiate this equation with respect to x, a into 1 plus b into dy by dx plus derivative of constant 0 is equal to 0. So dy by dx is equal to minus a by b of course. Okay, so that's how you can confirm slope is minus a by b. Or else you know this form y equal to mx plus c. If you try to convert that equation into y equal to some constant into x plus some constant, the constant which is in multiplication with x comes out to be minus a by b. Okay, that's how also you can decide. Clear? Yeah, minus a by b is the correct answer of course. 2. So anyway, so with this I would like to close the concepts of determinants and basically the matrix algebra, transformation matrices, whatever we have learned a lot. Okay, so if you just go for the PYQs, you can solve almost all the PYQs in this. Okay, then let's go to the concept of rank, the most important concept in matrices. Okay, why rank is very important, especially when we are trying to solve system of equations. Okay, so let's say I give you some system of equation. Rather than directly trying to solve the system, first of all you can check, if you know the concept of rank, you can check whether the system will have a solution or not. Okay, so let's say for example I have given you some system which do not have a solution. Okay, and let's say you're trying to solve you have started solving the question, then ultimately after some 15 minutes or 20 minutes, you'll find out this system cannot be solved. Okay, so this time whatever is spent in the process of identifying the solution, that can be eliminated if you know this concept of rank actually. Okay, so and normally this rank will again give to some other concept called null space or nullity. That's also a bit important. When we come to eigenvalues, we'll talk that in detail. Okay, so let's see what is a rank actually. Rank of a matrix. Okay, rank of a matrix. Rank of a matrix. Now let's see, a real number, in fact integer, R is said to be rank of a matrix A m by n. Rank can be defined even for rectangular matrices which are not square, of course. So A m by n if point number 1, all the minors of order r plus 1 cross r plus 1, I mean r plus 1 by r plus 1 are of A are zeros, all the minors of order r plus 1 by r plus 1 and above are zeros. Point number 2, there exists at least one non-zero minor of size r by r of A m by n. So this is how we define. So what is the concept behind? Sir, can you please tell how this concept of writing system of equations into matrix came? How we write like that? I'll tell you. Okay, so just give me some time. When I start, see today basically I thought of talking about rank and also system of equations, but I think okay, I'll introduce system of equations at least. We'll see how to convert a given system into matrix form. Okay, that's very much advantageous actually. Okay, so we'll see. This concept of rank is basically defined in this form, that if you take a matrix of size m by n, then any minor of size r plus 1 by r plus 1 should be 0, and any higher order minors should also be zeros, and there exists at least one non-zero minor of size r by r of A m by n actually here. Okay, like let's see, if you take a matrix A is equal to, so let's say I'm taking a matrix of size 3 by 4 for example. Okay, so 3 by 4, 1 2 3 minus 1 2 4 6 minus 2 maybe, then 3 minus 1 or 3 6 9 2, let's say. Okay, so this is a matrix. Now clearly you know it is of size 3 by 4. Okay, so this is of size 3 by 4. Now if you want to check the rank of this matrix, you should take minus of different elements. Okay, so how we'll actually calculate the minus? So first of all, this is of size 3 by 4, and you know minor is always a square, so the maximum size minor that you can take from this matrix is of size 3 by 3. Yes or no? Correct? Because it's of size 3 by 4, so it has 4 columns. So the maximum possible size minor that you can take out, or the maximum possible order submatrix that you can take out, is a 3 by 3 matrix. Okay, so if you check how many 3 by 3 minors you can do, so highest possible minors is 3 by 3. Okay, so 3 by 3 minors. So how many 3 by 3 minors you can form? You can actually form 4 3 by 3 minors to this matrix. What are they? Look, first 1 2 3 2 4 6 3 6 9, of course. Okay, then the second minor is, let's delete the first column, so 2 3 minus 1 4 6 minus 2 4 6 minus 2 6 9 2, of course. Okay, so this is the second one. Then third, coming to the third, actually we have, let's delete the second column, then 1 3 minus 1 2 6 minus 2 3 9 2, this is actually the third minor. And coming to the fourth minor, you delete the third column, we have 1 2 minus 1, okay, then 2 4 minus 2 2, 4, minus 2, then 3, 9, 2. Okay, so 3, 9, we have deleted the third column, right? So 3, 6, 2, of course. Okay, this is what we have. So these are the 4. So can we call a minor as submatrix or subset of matrix? The determinant of the minor is basically the can we call minor as the determinant of the submatrix is actually called the minor. Okay, it's not, see, these are determinants, they are not submatrices directly. Okay, this is different from determinant. Clear? So that's why the determinant of a submatrix is a minor. Clear? Now let's see, this is the determinant, of course. Now clearly, if we'll check as per this definition, the maximum possible order we can form for this given matrix is of size 3 by 3 we have formed. So there are total 4 3 by 3s which are possible. Now let us check whether if any one of them is non-zero. If any one of them is non-zero, then ultimately we have at least one non-zero minor of size 3 by 3. Will declare the rank of this matrix is 3. If all these are zeros, then we will go for the next size. Okay, because if 3 by 3 is failing, then we'll go for next 2 by 2. Okay, so that's how we will check. Now let's see, if you check the determinant of this matrix, this determinant is clearly 0 because second row is 2 times of the first row, third row is 3 times of the first row, it is 0 clearly. This determinant will also be 0 because this third row is actually 3 by 2 times of the first row actually. Okay, so you can see this, why this is 0 is second column is 3 by 2 times of first column actually, and I've told you if 2 columns are proportional or 2 rows are proportional, definitely this minor will be 0. You can calculate the determinant, it will come up to be 0 because clearly if you check these 2 columns, the second column can be obtained by multiplying a 3 by 2 to the first columns. Okay, 2 into 3 by 2 gives 3, 4 into 3 by 2 gives 6, 6 into 3 by 2 gives 9 again. Okay, so that's why this is 0. Same story here, this is also 0 because C2 is 3 times of C1. This is also 0. The reason is R2 second row is actually 2 times the first row, of course. Okay, so you can check R2 equal to 2R1. Sorry, didn't get you. So why is the determinant of the matrix 1, 2, 3, 4, 5, 6, 7, 8, 9, 0? Because this second row is actually 2 times the first row. So if these 2 rows are you have taken, then second row is 2 times of the first row. So these 2 rows are proportional to each other. So ultimately determinant will come up to 0. Clear? R2 is equal to 2R1 for AIM. Didn't get you. What is AME? R2 equal to 2R1 for second determinant. Yeah, of course, we can do that also. Correct. Okay, R2 is equal to 2 times of R1. Yeah, that can also be done because my main idea is to show you that it is 0. That's it. Okay, you can follow this C2 or O2s, whatever you want. No issues. Okay, then in fact R2 equal to 2R1 holds 3R1, R2 equal to 3R1 here, 2R1 here. Okay, they also R2 equal to R1 holds good for anything. Now let's see, all these are zeros. Now if all these are zeros, then the next possible maximum value is of size 2 by 2. Okay, so we will check 2 by 2s. So if you check 2 by 2s, how many 2 by 2s you will get? Let's see, total 2 by 2 minus you can pick is how many? There are 3 rows, so you can pick any 2 of them. 4 columns, so you can pick any 2 of them. So 3C2 is same as 3C1, 4C2, 4 into 3 by 2 into 1, this is 6. So total you have 18 minus. Okay, so if you try to take 2 by 2 submatrices from this matrix, you will get total 18 2 by 2 matrices. Okay, so out of this 18 2 by 2, if you have at least one non-zero determinant, then you can declare the rank of this matrix is 2. If all the 18 submatrices are singular, then ultimately we'll go for 1 by 1 again, and clearly 1 by 1 is at least you can have all non-zero elements, so definitely rank is 1 is what you will get. So first let us check whether we have any 2 by 2 combination such that the value is non-zero. If you check this 2 by 2 combination, if you check this 2 by 2 combination, then the determinant of this part is 12 plus 18, which is equal to 30. Okay, so should we take in the same order? Yes, first we'll consider the highest, then we'll start slowly decreasing the number of columns and number of rows in the matrix actually. Clear? 6 minus 2 9 2, yeah, of course, this combination. Okay, so this part if you take, intentionally I have made this, I did not make this element minus 3, I have made this 2 intentionally. So this 6 minus 2 9 2, if you take this block of 2 by 2, we can see there is a non-zero 2 by 2 minor in this total matrix. Yes or no? Rank should not be 0, it can be 0 if the matrix is null matrix completely. Okay, if the matrix is null matrix, then a rank is 0. Clear? Because you go 3 by 3, 2 by 2, even one by one you'll have a 0 element inside, so definitely rank is 0 for that matrix, for a null matrix. Okay, is this clear? So this matrix has got a rank is equal to 2. It is denoted by, you can write, it is rank is denoted by, I'll write a statement here, rank of A is denoted by row of A. This symbol you might have seen normally for resistivity, density, you can see all these things. Like when taking 2 by 2, so can we take non-consecutive elements? Yeah, 2. We see when we are forming 2 by 2, they need not be consecutive. Like for example, you take 3 by 3. Okay, in 3 by 3, only this first matrix is consecutive elements, consecutive columns. Okay, these 3 columns I have taken. If you take this, I have deleted this and I have taken this. Okay, maybe this is also consecutive. Now if you check the third thing, I have deleted the second column and have taken first, third, fourth columns, which are non-consecutive actually. Okay, so that's why you can choose even non-consecutive elements from non-consecutive rows or non-consecutive columns. Clear? Yes? Is that clear to all of you? Rank is 0 only for null matrix. Yeah, of course. Because if you take any matrix other than null matrix, you'll have at least one non-zero element. That means you have at least one non-zero minor of size 1 by 1. Okay, so that's what. Clear to all of you? Okay. Is this clear to each and every one of you? Please type in the chat box. I'll have some water meanwhile. So can anyone tell me what is the rank of this matrix now from this definition and from these explanations? Oh, sorry. From these definitions and from these explanations, can anyone tell me what is the rank of this matrix now? From this definition and from these explanations, can anyone tell me what is the rank of this matrix? So how you calculated total minus? Please tell one more time. Yeah, I'll tell you, Shashwata, just a minute. Fine. Okay, so let's see how I calculated the total minus. Here 2 is the rank because you can clearly have a 2 by 2 non-zero element. Okay, so that's what. And then first of all, how this 18 came? You know, if I want to form a 2 by 2 matrix, out of these 3 rows that I have, I can select any 2 rows. Yes or no? Correct. Out of these 3 rows that you have, I can select any 2 rows. And out of 4 columns available, I can select any 2, so that I have 2 rows and 2 columns, so that I have a 2 by 2 matrix. So the number of ways in which I can select 2 rows out of 3 is 3C2, and number of ways in which I can select 2 columns out of 4 columns is 4C2. Okay, so 3C2. After selecting those, the task is not finished. So multiplication into 4C2. So 3C2 into 4C2 gives 18. That's it. Okay. Are you all clear with all these points till now? Please type in the chat box, each and every one. Is it understandable to each and every one of you? Is it understandable to each and every one of you? Till this point, is it clear to all? Should learn probabilities are here. Yeah, definitely. I'll teach probability after you know, this complex calculus. Yeah. Okay. So everyone should type in the chat box. Dhanush, Vasista, Sagnika, every one of you, please type in the chat box. It's clear, right? To all. Now, let's move on to a very important form, which is called the row echelon form of a matrix. Okay, so row echelon form of a matrix. Row echelon form of a matrix. why this is important? Okay, so why this is important actually? So let's check. Why this is actually important is, when I give you a matrix, doing these calculations is not very comfortable, yes or no? Because of course it's of size 3/4, so it's happy, at least we have put some effort and we have calculated, and we figured out total there are 18 number of 2×2s, and it's really tough. Of course, if I have given a very simple matrix, because intentionally I have shown you that this is 2 times of this, so ultimately you can identify which determinants are 0 and you can spot one block which is non-zero. But let's say if I give you some complicated matrices like 1, 7, -8, -4, 2, 9, these kind of elements, then ultimately this calculation becomes very very non-intuitive. Okay, we should actually do a lot of things to tell whether the determinant values are zeros or non-zeros. So to compensate that, what we'll do is we achieve at some form which is called row echelon form of a matrix. Okay, so how we achieve this row echelon form and how we'll actually decide the rank, okay, we will see now. Let's see. Row echelon form of a matrix. A matrix A, capital A, is said to be in row echelon form, if, okay, so a matrix capital A is said to be in row echelon form if number of zeros before the first non-zero element in a row is strictly greater than number of such zeros in its preceding row. Okay, or maybe you can say less than its succeeding row, that's also the same. The second point here is 0 rows, if any. Let's say in a matrix, if you get any 0 rows, for example, 0 rows, if any, should lie at the bottom of the matrix. 0 rows, if any, should lie at the bottom of the matrix. Like for example, I'll just give you examples, then we will see how to convert any matrix into echelon form. Okay, so example, A is equal to, this is of the form A, B, C, D, 0, E, F, G, 0, 0, maybe you can keep one more 0 if you want, or else H, I, let's say. Okay, so this is a matrix. Then let's see, all these elements are non-zeros. Okay, A to I, all these elements are non-zeros, let's say. Okay, you can see A not equal to 0, we'll keep that, A not equal to 0. Now if you see this matrix, what happened here is, this is in this row, the first row, the first non-zero element is A and you don't have any 0 before this. Okay, in the second row, the first non-zero element is E, let's say E not equal to 0, for example. Okay, then this is the first non-zero element, and here also let's say H is not equal to 0. Then we have, if you take these 3 rows for example, in this first row, this is the first non-zero element, and number of zeros before this first non-zero element is 0. We don't have any zeros. Okay, so when you come from this first row to the second row, this is the first non-zero element, so before the first non-zero element you have 1 0. Okay, so here in the first row you don't have any zeros before the first non-zero element, so definitely in the second row you should have minimum 1. Okay, and we have 1. Now since here you have 1, in the next row you should have minimum 2. Okay, so that's why we have minimum 2 zeros before the first non-zero element. So that's why we can say this matrix is in row echelon form. Or else you can also have another thing like 2 minus 1, 2 minus 1, 0, 4, then 0, 3, 0, 7, double 0 or triple 0, 4. This is also in echelon form because number of zeros before the first non-zero element. Okay, so this is the first non-zero element, there is no 0 before this. Then here the number of zeros is 0, Then when you go to the second row, this is the first non-zero element. If this is the first non-zero element, since here it is 0, it should be at least 1. We have 1. Okay. Similarly, when you go to the next row, this is the first non-zero element. So since here this is 1, it should be at least 2 in the next row. So we have 3. So this is also in Echelon form. Okay. Or as I told you, if you have any 0 rows, for example, 0, 3, 4, 0, for example, then 0, 0, 7, 8, let's say, then let's say you have complete 0, then this is how. This is also in Echelon form. So that's how we will see how to convert matrices into any one of these forms. We will see how to convert. But this, if a matrix is in this particular format, we say this is in Echelon form. Okay. And what is the advantage of having Echelon form is number of non-zero rows in a matrix is called the rank of the matrix. Okay, in Echelon form, of course. So let's see if the number of non-zero rows in row echelon form of a matrix is equal to its rank, actually. Okay, so this statement is really an important statement. Number of, clear? So number of non-zero rows in the row echelon form of a matrix is actually equal to the rank. So if you, by doing something, okay, we'll see what is that. By doing some things, if you can bring a matrix into this form, for example, into this echelon form, then just by looking at the number of non-zero rows, you can tell what is the rank. You need not check the determinants of each and every possible combination like you have done in the previous case. Did you all understand the advantage? First of all, did you all understand advantage of why we convert to echelon form? We'll see how to convert, we'll see. But did you all understand why we are converting? Because if you have a matrix in the echelon form, just by visual inspection, you can tell what is the rank of that matrix. Clear to all of you? Yes or no? Please type in the chat box. So please type in the chat box. Is this clear to each and every one of you? 7, Kids Gaming, Abdul, Danush, Asad, Thomas, Vasishta Arya, Hi Krishnan, Shashwata, Vivek, and a lot of names, of course, I couldn't read. Yes? Okay. Now, let's see how we convert. Okay. So how to convert a matrix into echelon form? That's the next question then, ultimately. How to convert a matrix into a row echelon form. How to convert a matrix into a row echelon form? So let's see. For example, in this case, you identified rank of A is equal to 2. Okay, so you have got that rank of A is equal to 2. Okay, so we have identified by a lot of determinants and all. So this is 2. So let's see how we can get this value of 2, of course. Okay, hi Prabhuteja, look here. If you take this A, or in general, if you take any element, A is equal to, I'll tell you the generalized thing first of all. A11, A12, A13 and so on, A1n for example, A21, A22, A23 and so on, A2n and so on. Let's say you go till M1, M2, M3, AMN. Let me write one more column so that you can, one more row, you can have some understanding. Okay, so this is the matrix. Now, if you have this matrix, then let's see. In this case, firstly, if you want to start with echelon form, one thing that we do is we try to make this element zeros. Okay, this is zeros. So to make this element zeros, to this row, we apply the transformation. R2 changes to R2 minus A11 or A21 by A11 into R1. If you perform this transformation, definitely this matrix will have this element 0. Yes or no? Because this element gets converted to A21 minus A21 by a11 into a11 is what you'll have. So this term gets cancelled. a21 minus a21, you'll have 0, of course. Okay, so this is what you'll get. So by performing this transformation to this second row, this will make this a21 will be 0. Okay, and similarly it will also change all these elements. Okay, so it will also change a22, a23 as maybe some other elements, a22 dash, a23 dash, some other elements. Okay, similarly for the third row we apply the transformation. For the third row we apply the transformation. R3 changes to R3 minus a31 by a11 times R1, and this, if you proceed, finally you have Rm changes to Rm minus am1 by a11 times R1. This is what you will have actually. If you perform these transformations, if you keep performing these transformations in a single go, you will end up with all these elements as zeros, of course. Correct? Yeah? Yes or no? You'll end up with all those elements in the first column below a11 to be zeros, right? Now one question that comes up first of all is, what if this element is 0? Correct? If a11 is 0, then what happens? Ultimately you cannot do this division because division with 0 is not defined. Okay, division with 0 is not defined, so ultimately you cannot do that division actually. If a11 is 0, then how to do? What we'll do is, you can swap. Okay, so let's say for example you have 0 here but you don't have 0 here, then first of all, before performing this complete operations, you can swap these two rows and make sure this a11 is non-zero. Okay, then the issue gets resolved and you can perform this transformation. Clear? By performing these transformations, this leads to a matrix which looks something like A is equivalent to, then A is equivalent to, let me just write this a bit clearly. This first row do not get changed, a12, a13 and so on, a1n. But coming to the second row, this all elements are zeros, of course. Then these elements get shifted to a22 dash, maybe some different variable which is equal to, it gets converted to a22 dash, of course. Okay, so because this element gets converted to a22 minus a21 by a11 into a12, so which gives you some different number. So do we have to use only a11 or can we use a31 or no? Because according to the Echelon form, the number of zeros should keep increasing. So first of all, if you don't disturb this, then this having zeros will actually make your things towards Echelon form actually. Okay, that's why. So swapping doesn't change anything? No, it doesn't change. Okay, because I'll tell you, sir, at the end of the class, please repeat this Echelon topic once in short. Okay, no issues. Okay, so this is a22 dash, then similarly this is a23 dash and so on, a2n dash. Similarly, all these elements will change, a32 dash, a33 dash and so on, a3n dash and so on. This goes on. Now, if you want to convert this to Echelon form, of course, then what you can do again here is, now compared to the 0 here, you should have more zeros here. Okay, so let's say these all are non-zero elements. Then compared to the zeros here, like this is the first non-zero element, you have 1 0. So before the first non-zero element, you should have minimum 2 zeros. That means you should make these elements and all these elements zeros. So how you will do? From the third row, you will start the transformation. R3 transforms to R3 minus a32 dash by a22 dash times R2. This transformation will definitely again give you this elements zeros, of course. Okay, so rank remain unaffected while interchanging rows or columns, but it does have effect on determinant calculation? No, because rank is decided whether based on the value of the determinant is 0 or not, or basically value of the minor is 0 or not. Okay, by swapping rows, if you interchange two rows, only the sign changes. Okay, so if for example initially the determinant value is non-zero, by swapping those you have negative of that number, that's it. But non-zero number do not get converted to 0. Okay, so that's why rank will not get affected by doing row swapping. Clear? Did you understand? In last class when I'm teaching properties of determinants, I have told you if you swap two rows, the sign of the value changes but the absolute value remains same. Okay, so if you interchange two rows, only the sign changes, and if it is non-zero determinant, ultimately even by interchanging rows you will have a non-zero value of the minor. Okay, maybe it's positive or negative, doesn't matter, but it will be a non-zero. Non-zero remains non-zero. Okay, so that's what. Got it? Did you understand this? swapping this will not affect the rank. Yes. Okay. So we are repeating this. Okay. So if you repeat this, finally there comes a situation where you'll actually end up in a row echelon form. Let us work it out for one example. Example: A is equal to 1, 2, 3 minus 1, 2, 4, 6 minus 2, then 3, 6, 9, 2. This is what I have taken. Okay. And you found out rank of this is 2 by inspecting a lot of things. So let us try to convert this into row echelon form. Okay. Converting this A to row echelon form. Converting A to row echelon form. So let's see how do we convert. Okay. So let's see how do we convert actually. So first my intention is to make these two elements zeros. So let us apply the transformations. R2 changes to R2 minus A21 divided by A11, which is 2 by 1 times of R1, which is nothing but R2 minus 2R1. R3 changes to R3 minus, similarly 3 by 1 times R1. So this is nothing but R3 minus 3R1. Okay. If you perform these two transformations, such 2 times swapping doesn't change sign also. Yeah, correct. Even number of times if you perform this interchanging operations, that sign also gets restored. So anyway, let's see. So if you perform these two operations, A will be equivalent to 1, 2, 3 minus 1. Then R2 minus 2 times of R1. 2 minus 2 times of 1. So 2 minus 2 gives 0. Okay. Then 4 minus 2 times of 2 will again give you 0. 6 minus 2 times of 3 will again give you 0. Minus 2 times minus 2 times minus 2 times of minus 1, which is again 0 of course. Okay. Then coming here, this 3 minus 3 times of 1, 0. 6 minus 3 times of 2, 0. 9 minus 3 times of 2, 3 times of 3, 0. 2 minus 3 times of minus 1. Okay. So 2 minus 3 into minus 1, this is 5 of course. Now this matrix is not in row echelon form because this 0 is on the top. Okay. So we'll apply one more transformation. Let us interchange R2 and R3. So if you interchange R2 and R3, then this matrix becomes A equal to 1, 2, 3 minus 1, 0, 0, 0, 5, all zeros. Now this, it is in row echelon form. It is in row echelon form. Okay. So that's in row echelon form. You can see clearly this is the first non-zero element in this row and there is no zeros before it. Okay. So since there is no zeros before it, in the next row before the first non-zero element you should have at least 1 0. Okay. So this is the first non-zero element, you have 3. So there is no issue. Now number of zeros before the first non-zero element here should be less as compared to the next row. So here all 4 are zeros. It is in row echelon form. Now in this row echelon form of this matrix, you have 2 non-zero rows actually. Okay. Because you can see this element is non-zero. So definitely this is also a non-zero row. All the elements are not zeros here in this case. So that's why we have 2 non-zero rows. So this implies row of A is equal to number of non-zero rows in row echelon form, which is equal to 2 of course. Okay. So which is equal to 2. This method looks very simple to be frank, and at the same time when the size of the matrix is very large, okay, practically checking each and every possible minor determinant is not possible for us. Okay. So let's say if I give you 300 by 400, okay, then practically taking sub matrices of size 3 by 300 by 300 and checking determinant like that, doing from multiple combinations cannot, it's not physically possible. Okay. But this algorithm whatever we have written is valid for any of the whatever the size you give. Okay. So you can write a computer program simply performing this particular transformation and you can do. Okay. Clear to all of you? You can, in fact, you can do all these things by using a simple for loop. Yes or no? For I equal to 1 to n, if I write for I equal to 1 to for I equal to 1, I less than or equal to n, I less than or equal to n, I plus plus, if I write R I is equal to Ri minus, since we define the elements initially, Aij by A11 in the initial part times R1. If you write this transformation, for example, okay, so Ri is equal to Ri minus Aij by A11. This is just a, I'm just giving you some pseudocode so that you can understand and convert it to algorithm. So A11 into R1, here also you can keep 1 basically, okay. So this is 1. Then you can see by performing this for loop, you can convert all these rows R2. First of all, for equal to, okay, let's say we'll start the loop from 2. So 2 to n is what you can have, because it depends in different platforms. In MATLAB you cannot go below, I can start from only 1, okay. So we can, if you go with 2, then this loop will actually first perform this second transformation, third, fourth, 5, 6, it clears all the lines, okay. Then when you go for the next matrix, you'll get the next matrix, of course. Then you can write one more thing, okay. That's how if you write loops in loops, nested loops, then this complete algorithm can be done very easily, okay. But anyway, right now I'm not going to look at this, but just want to explain you, okay. Is this clear to all of you? Okay, is everything understandable here? Why we are converting into echelon forms and why those echelon forms are actually important? Is this clear to each and every one of you? Yes or no? Please type in the chat box. Okay, everyone whoever is on live, please type in the chat box. Is it understandable to you or not? Each and every point. If you have any difficulty at any point, please let me know. I'll be happy to clear. Okay, Bablu, Vivek, yeah. So this is how we actually convert into echelon forms. And anyway, if you find the leading element, basically it's called the pivoting elements. Whatever the elements you are using here, basically exactly in the denominator, those are called pivoting elements, okay. And if those pivoting elements are zeros, we'll avoid this pivoting by just what do you say, swapping those. So is column transformations can be done? Practically no, okay. Only row transformations can be done. The reason for that is, normally if you want to convert this you can do, but practically we'll use this echelon form for solving linear systems, okay. In solving a linear systems, you should always try to get only in terms of echelon form. The reason is, see, I'll tell you. Anyway, just give me 5 minutes. I'll move into system of equations. I'll clear there, okay. So some properties of rank is what I should tell you now. Properties of rank. So, you know, first, rank of A of size m by n is less than or equal to minimum of m comma n, of course, okay. So because you can see, if this is of size 3 by 4, then rank cannot be 4, okay. Maximum it can be 3. So the minimum value of these two is actually here. So rank of A of m comma n is less than or equal to the minimum of these two numbers, okay. Because you have seen, we have taken a 3 by 4 matrix in the previous example, for which we have got the rank is equal to 2, correct. So this 2 will be definitely less than 3, okay. Because if this is of size 3 by 4, the maximum possible order you can form is 3 by 3. So that's why this side is minimum of m comma n. So the minimum of these two numbers is on the right hand side, and rank of this A m by n will be less than or equal to that, clear. And let's see one more properties, in fact 2 more I think you can see, nice properties. Rank of A is equal to rank of A transpose, because you know determinant of A, or basically any minor of A, will be same as A transpose, okay. So the things do not change. So the determinant of any 2 by 2 or any 3 by 3 at any stage, you try to calculate the rank of A, or you try to calculate the rank of A transpose, they both give you the same thing, clear. And third, if you have multiplication, rank of product of two matrices will be less than or equal to minimum of rank of A comma rank of B, of course. The reason, this is actually very important property, to be frank, especially when we are dealing with partition matrices or something. This is very appreciable. You have checked, product of two non-zero matrices can still be a zero matrix, okay. Like for example, you can see, let's say the rank of this is 1, okay. So clearly rank is 1 because this is non-zero. Similarly, you take here, this rank is also 1 because B is non-zero. But if you multiply these two, you get a null matrix. This is 0, okay. So 0 is less than 1, of course, clear. So that's how you can have cases where rank of this product AB is less than or equal to minimum of the rank of A and rank of B individually. Clear? This can be proved, of course, by taking initial notations and all, but right now I'm not doing that. Okay, I'm just giving you the properties. Clear? Yes or no? Now we'll solve 1-2 questions so that we will have some better understanding. Okay, so let's see. Sorry, there's some comments. Repeat in short, sir. Yeah, basically this echelon form, what we are trying to do is, this matrix is said to be in echelon form if number of zeros before the first non-zero element should keep increasing down the matrix. Okay, like you can see in this case, we have seen number of zeros before the first non-zero elements keeps increasing. Like here there is no 0, here there is 1, here there is 2. So this should keep on increasing, and for that to happen, we develop an algorithm which makes you have that echelon form finally. Okay, after doing all the calculations. Clear? That's what we have done actually, and I have worked out with an example. So let's solve some questions which could help you a bit. So solve this question. I'm giving you some time, of course. So single choice, no, integer type. Okay, it's a 3x4 matrix, and I'm giving you 150 seconds. Okay, so start. Come on, solve this faster. Be fast. Okay, so it's a 3x4 matrix. So this might sound naive, but I still didn't understand why that sign change while interchanging rows or columns, but the rank does not. Sorry, it's okay. I'll explain you. Just a minute. Let's solve this question. First calculate this. I'll tell you then. Faster, fast. It's not 0, yeah. You can see clearly non-zero elements. Minimum it should be 1, no? Why you are telling 0? I have given you 150 seconds, which is good enough. You can solve. 2.5 minutes. Three, 2, okay, maybe possible, quite possible. Okay, even I don't know, I have to solve to tell you, but three is coming, maybe possible. But one thing I can say is it's not 0. Okay, definitely it should be minimum 1. Okay, the poll is ending up fine. So let's figure out what is the rank. Let A is equal to 5, 3, minus 3, minus 1, 3, 2, minus 2, minus 1, 2, minus 1, 2, 8. Okay, again this is a previous year question. So let's see, let us follow a classical algorithm to convert this to echelon form. Okay, because practically checking the determinants and all could be very calculation heavy. So we'll do one thing. Let's say R2 changes to, because my main focus is to make these two guys zeros. So let's say R2 is equal to 3 minus 3 by 5 times R1, or we can also do 5R2 minus 3R1. Okay, that's also fine, because R2 minus 3 by 5 R1 will make this 0. Similarly 5R2, because if you take LCM, 5R2 minus 3R1 will also make this 0. Similarly R3 changes to 5R3 minus 2R1. So let's say you have this. This tells you 5, 3, minus 3, minus 1. Then ultimately 5 3s are 15, minus 3 5s are 15. 15 minus 15 gives you 0. Then 5 2s are 10, minus 3 3s are 9. So 10 minus 9, 1. Minus 10 plus 9. minus 1. You have to be a little careful, okay, when you are performing these calculations. If one element goes wrong, everything goes wrong, okay. So you have to be a little careful. Minus 10 minus of minus 9 plus 9. So this is minus 1. Then minus 5 plus 3 minus 2. Coming to the last row, 5R3 minus 2R1. So 10 minus 10. This is 0, okay. So this is 0, of course. Then minus 5 minus 6 minus 11. Then 10 plus 6, 16. Then 40 plus 2, 42. This is what you have, okay. So this is 42. Now let's see, if you want to, this is not an echelon form, okay, because here there is no 0 before the first non-zero element, here there is 1 0 before the first non-zero element, and here also there is only 1 0, but I strictly told you, I told you it should be number of zeros should be strictly more, okay. So here if it is 1 0, here it should be minimum 2. So that means it is necessary for us to make this element is also 0. So we'll apply one more transformation. R3 changes to R3. So we'll use this element. So it is 1. So plus 11 R2 is what we'll do. Okay. So R3 plus 11 R2. Now if you do this, we have A will be of the form 5, 3, minus 3, minus 1. Then 0, 1, minus 1, minus 2. And coming here, 0 plus 11 times of 0. Okay. This is again 0. The reason is why I'm using R2 is, you can ask me why not R1. If I use R1, again this 0 get disturbed and we'll again get non-zero here, okay, but we don't want that to happen. Clear? Why I'm using only R2, why not R1 is because if I use R2, this 0 will again get distracted, okay. So that's why. To keep this 0 as 0, I'm using R2. Then minus 11 plus 11 into 1, this is also 0. Then 16 plus 11 into minus 1 is 5. And then after 42 plus 11 into minus 2, so this is 20. So clearly you can see this is in row echelon form. This is in row echelon form, and ultimately the number of non-zeros in this is 3. So we can multiply scalar to the row which is being transformed. Yes, you can multiply, no issue. Can we stop at this point and there only one expanding along C1? Calculate determinant manually is non-zero. Yes, you can do it. Okay. So like for example, you can take this 3 by 3 and if you found it's to be non-zero, you can do that. No issue. Okay. But that's like probability based. Okay. What if first you get 0, then second you get 0, and let's say if for the fourth determinant you're finding it's non-zero, then it takes so much time. Okay. So that's what. Clear? So here just a couple of transformations will bring to this form, and this is in row echelon form actually. Okay. And number of non-zero rows is equal to 3. This implies your rank of A is also 3 actually. Okay. Did you understand why I'm not taking determinants? Okay, maybe in this particular matrix you may have the first determinant itself as non-zero. Can we just multiply? Yeah, you can multiply, no issue. Okay, so a non-zero scalar multiplication will never change anything. That's a transformation. You are transforming your, okay. Let's say for example, if these are the elements, then you are transforming that, right? Okay. So you can see from here onwards, I'm not keeping the sign equality. It's a transformed matrix. Okay. That's what. Clear to all of you? So this is basically 3, and you can check. We have done basically in this row echelon form, and we have done transformations. Even if you are multiplying a scalar, you are trying to change the row, so that's a transformation. It's counted as transformation. Okay, Hari Krishnan. Okay. Here you can ask me why not I consider 3 by 3. But if I consider 3 by 3 and calculate, okay, maybe I can get 0. I can get non-zero. Okay, but if I get 0 and if I start checking other elements, then it takes some time. Okay, that's why. But this is a procedure which guarantees a solution within 2-3 transformations. Okay, like 1 step and 2 steps. That's it. Okay, so that's why it's always better to follow a path which guarantees you a solution. Okay, that's the idea. So come on, tell this. So basically in this question it's 3. So 50% of you have answered that. Vivek, Arya, good. Anyway, let's go to this question. So two matrices A and B are given below. A and B are this. If rank of matrix A is n, then the rank of matrix B is what is? Okay. So single choice again. 150 seconds I'm giving. Start. Any shortcut for equivalent forms? Are no. Okay, we have to do it. We have a lot of algorithms. In fact, when the matrix size is very high, but we do that. If A and B, if rank of matrix A is n, then what is the rank of matrix B? That's what they're asking. C, B, okay. Fight going on between B and C. Good. Come on, do it quick, faster. Maybe this is the last question we'll deal today. Time is up. So B equal to A transpose, is it? Come on, faster. C. B equal to A transpose, rank of A equal to rank of A transpose equal to n. Good. Yeah, of course, you have identified this point. Good, actually. B, C. Still, I need some more options. Okay, give. A, D, no one is interested. Why, poor fellows? Only B and C. One out of B and C. Abdul, Ashwini, Vivek, Sagar, Harkrishnan, Vivek, Arya, Pandian, Basit, Lokesh, 7, Samiksha, Kids Gaming. Okay, the time is running up. I had solved the earlier, otherwise no idea. Good. Okay, fine. Experience, huh? Chalo. Let's see. So first I'll tell you one idea, then we'll discuss the second method also, as people are telling. So firstly, it's a 2 by 2 matrix. Okay. If you consider that A, this is PS minus QR, of course. Okay. So this is PS minus QR. Now if this is 0, then ultimately rank is 1. If this is non-zero, so is it not possible? Because D is not possible because it will be greater than the order of matrix. Okay, yeah, of course. 2n is not possible. That's fine. I'd solve this. Okay, yay. Okay. So let's see. Det A is equal to PS minus QR. Okay, so directly you can calculate. It's a 2 by 2. So simply you can calculate that. Now, rank of A can be 2 or 1. Okay, and normally if all these elements are not zeros, then it is not 0, of course. Okay. Let's see if you calculate det B, what happens? Det B is equal to P square plus Q square into R square plus S square minus PR plus QS whole square. Okay, so this is actually a symmetric matrix, PR plus QS whole square. If you expand this, let's see what you get. P square R square plus Q square R square plus P square S square plus Q square S square minus, if you expand this, we have P square R square plus Q square S square minus 2PRQS. This is what you would have got actually. Okay, this is what you have got. Now if you simplify this, this first term and this term cancels, this Q square square and this plus Q square square also cancels. We have the terms like P square S square plus Q square R square minus of minus again plus, oh sorry, this is plus, right, because it's plus whole square, so this is plus, so minus of plus is actually minus. This is, just a minute, this is plus, of course, because it is plus square, so minus of plus, now it is minus. Minus 2 times of PQRS is what you have, so I can write this as PS into RQ or QR maybe. So this can be written as PS minus QR whole square. Okay, so determinant of B is actually again PS minus QR whole square. Now tell me one thing, this means this is nothing but det A whole square is what you got. So if this is det A whole square, now if det A is 0, this is also 0. Okay, this is also a 2 by 2 matrix. which means if this is a singular, this matrix will also be a singular matrix. If this is non-singular, then this is also non-singular. So that means this rank of A is depending on this, which is same as this det B is depending on this term. Okay, and these two are same, of course, PS minus QR. That means wherever this term or basically this rank gets stopped, at the same location this rank of B also gets decided. So rank of A and rank of B both has to be same, because both are depending only on the value of PS minus QR, and clearly option C is the correct answer. Okay, so I mentioned order of matrix so that we can know how many elements are in the matrix. They are mentioned, no, clearly it's a 2 by 2. This is also a 2 by 2. Okay, maybe because of the spacing you have got confused. Okay, maybe it's a typing issue, but P square plus Q square, PR plus QS. Okay, I understand. Okay, there is a concern, but basically this is P square plus Q square and PR plus QS. This is a 2 by 2 matrix again. Okay, now so this is, now as some of the others are telling, if you slightly inspect, this B is actually A times A transpose. Okay, in this case. Okay, clear? Of course, this is a bit, you have to be a bit intuitive to understand this, but even if you don't know this, you can do it in this way. 2-3 steps could give you answer. Less than 2 minutes is required to solve this. Now if you see this, then ultimately determinant of B is equal to determinant of A whole square, which is this. Okay, so that's the shortest way of understanding. Okay, no issue. Okay, I think some typing issue happened here, but it's okay. I'll make sure there's no typing errors. So det B is equal to det A whole square. Okay, so if you have this det B is equal to det A whole square, which is the same thing, then ultimately again you can decide that rank of A and rank of B will be mutually same, because they depend on the same term, PS minus QR, or basically determinant of this matrix. Okay, fine. Is this clear to all of you? Did you understand why this is n? Here if you want, you can write, of course, as one more property, that fourth property is rank of A is same as rank of A transpose, or maybe rank of A transpose A, of course. Okay, fine. So maybe I'll stop here for today. So I'll give you some homework questions. So this is actually a homework. So they're telling A and B are two matrices such that A is this and B is not equal to 0 and AB equal to 0. This is non-zero and this is 0 and AB equal to 0. Rank of matrix B is dash. Okay, so this is one question. So this is what you have to decide. Rank of matrix B. This is smaller. Okay, then just a minute. So let's go to the next question. This matrix vector, the number of distinct real values for which system of infinitely many solutions. Okay, you leave this because these two questions are from system of equations, which I was not able to cover today, but we will cover that. Okay, so this is one question which you have as homework for today. 7. Sir, do not possible because it will be greater than the matrix. What's your question? 7. Just let me roll the comments. Previous comment. 7. Sir, this might sound, but I still didn't understand. Dead sign. Yeah, got it. Okay, so see, if you go for this matrix, for example, okay, I'll show here this example. Okay, so let's say you go to this example. Now let's say this rank is 2 because it's a 2 by 2 matrix. Clearly I mean the first non-zero minor is coming out to be of size 2 by 2. Now let's say I have swapped these two, for example. Okay, so 7, look here, let's say I have swapped these two rows, for example. If I swap these two, what happens is in the sub matrices this gets swapped, these two get swapped, these two get swapped, and these two get swapped. But because of this swapping, this determinant being 0 will not get changed. Yes or no? Can you understand? This determinant is 0. If I swap this, it will be minus 0. That's it. Okay, because this one swapping gives a minus sign here. So minus 0 is same as 0. So that's why this 0 remains 0 here. Okay, and let's say if this is non-zero, for example, let's say it is 2, for example. Okay, if I swap this, this becomes minus 2, but 2 never becomes 0 actually because of swapping. Okay, 2 becomes minus 2, but 2 never becomes 0 actually. Okay, because of swapping. That's why because of swapping, non-zero minus stay non-zero and 0 minus stay 0 actually. So there is no difference. Clear? That's why when you run this process for 3 by 3, 2 by 2 and all, your rank will never change. Understood? Because of swapping, only sign of the minor changes, not the value of the minor. Got it? That's what. And if your minor is initially 0, it stays 0, and if it's non-zero, it stays non-zero. Clear to you? Yeah? Okay, good. Fine. I thought of covering system of equations also today, but anyway, it took some time to solve homework, previous homework, and these things. Fine. Anyway, so today you have one homework question. Actually, system of linear equations I'll start tomorrow. I'll touch up tomorrow maybe. So 2 minutes summary if I would like to give. I'll give you today we have talked about transformation matrices in the beginning. And we have also discussed the concept of rank and how to calculate it. Okay, so we have discussed this. One more question I would like to give homework. If you are free, you can just, not if you are free, you should do this. So this is also a homework question. Okay, from determinants. Clear? So this is a homework question from determinants. Which one of the following does not equal to that particular determinant? Okay, so these are 4 determinants. So out of these 4, which is not equal to that particular determinant, and all these are PYQs. Okay, so doing transformation doesn't mean it remains same matrix, right? Value of determinant, rank, etc. remains same. Yes, that's it. Okay, we do transformation to find determinant and rank only, right? Yes, of course, because matrix do not remain the same. Clear? And I'll tell you why row transformations will not change the properties of the matrix actually. Okay, that for that to be understood, we'll talk in the system of equations that we'll see in the tomorrow's class. Okay, because physically today I'm just playing with some matrices. Okay, but I did not physically tell you how a system of equations can be shifted to a matrix form. That we'll do tomorrow. So that's when you'll understand why row transformations do not affect the properties of the matrix. Clear? Okay, fine. So anyway, so this question is for homework today, and this question is also for homework today. That's it. We have 2 questions because I was not able to start this system of equations. Fine then. So again, we'll meet tomorrow at 7 PM because tomorrow is again Friday. So we'll meet again at 7 PM for this session, and we'll introduce system of equations. So tomorrow's class is really important. Okay, because why we are learning all the matrix algebra, why we are learning all the matrix stuff is basically one of the simplest applications is to solve linear systems. So we will start actually solving linear system of equations tomorrow, and maybe in tomorrow's class we'll also start eigenvalues. Okay, so it's really important. Clear? So daily 7 PM, and of course the batch is going to be in English. So please do attend tomorrow at 7 PM sharp. We will start system of equations. Okay, and please solve the homework that I've given you for 2 questions. Clear? Any questions or anything that you say? So how the course is going on? It's been 4 lectures. So you want me to change something or speed or maybe anything that if you have any suggestions, it's fine. Are you all liking this course? Are you all finding it useful? When is batch coming? GW. Just wait for the updates. There will be regular updates on our YouTube channel, so you can get good information. Okay, so after you complete maths portion, you will be continuing with other topics like algorithms. No, I don't take that because I have other things to work with. Okay, so fine then. We'll meet tomorrow at 7 PM tomorrow, and we'll meet tomorrow at 7 PM, and more number of multi-solution approaches for PYQs. Yeah. Okay. Fine, that's one point. And what else? See, basically, rather than teaching more number of multiple solution approaches, what I'm teaching is the optimum way of solving. Okay. For majority of the times, you cannot go for a solution which is less in time than what we compute in class. Clear? So fine then. Thank you all. We'll meet at 7 PM tomorrow, and we'll start with system of equations. Thank you all.